Hello students, in this video we'll define the Riemann curvature of a manifold. So given the Riemann tensor, Christoffel tensor, R, I, J, K, L, we can form an invariant and what's the invariant going to be? It's going to be R, I, J, K, L, and I'll have an A, capital I, covariant, a contravariant vector A, I, A, K. Then I'll have a B, J for another vector, B, J, B, L, right? And so this is an invariant. And then I'll also construct a different invariant, construct another invariant. So this invariant, of course, depends on these two vectors, A and B, which generate a plane, basically, right? Okay, excellent. Construct another invariant, which is going to be what? It's going to be G. I'm going to do an IK, G, L, J, L, minus G of IL, G of IL, G of JK. And I'm going to apply this to the same expression over here, to the A, I, A, K, B, J, B, L, like so. Okay, so these two invariants, and now both of these invariants over here exhibit symmetry structures, right? So what do we have over here? So we recall that we know that R, I, J, K, L is negative R, J, I, K, L. I know that R, I, J, K, L is negative R, I, J, L, K. I know that R, I, J, and then what? And then KL is going to be R, K, L, I, J. And then I know the Bianchi identity, that R, I, J, K, L plus R, I, K, L, J plus R, I, L, J, K is equal to 0. So these are the symmetries of the Riemann tensor. And you can actually check that if we look at this expression over here and call this expression over here T, I, J, K, L, then T satisfies these identities over here star, right? Then, because it has a determinant, the structure of a determinant, right? Then proposition is that T, I, J, K, L satisfies all the star relations, satisfies all of the star relations. Which means if I look at the ratio of these things, I'll have a pure invariant, right? And so now what we're going to do is we're going to construct this. So let's build K of A and B, basically. These vectors A and B, I'm just going to write them sort of symbolically as A and B, right? For contravariant AI, BI, like that. Contravariant things is going to be what? It's going to be my Riemann tensor, I, J, K, L, A, I, A, K, B, J, B, L, over what? Over G, I, K, G, J, L minus G, I, L, G, J, K applied to the same thing. A, K, B, J, B, L. Sometimes this is referred to as the sectional curvature, right? So in more advanced text, you're going to see this called the sectional curvature. And this sectional curvature is independent of the coordinates, right? So since we have all the relationships satisfied, they're in the same space, and so this is up to, so K is independent of coordinates. This is independent of coordinate change. Beautiful, okay? And so this K is called the Riemann curvature. So K is called the Riemann curvature. Now, of course, a special case of this Riemann curvature comes in the case when we're in two dimensions, right? So recall, when the dimension is equal to 2, we only need have one independent component. that component is R1, 2, 1, 2, right? So for a two-dimensional space, we have that K will be R1, 2, 1, 2 over what? Over my, so you have I, so I'll have a G1, 1, G2, 2, minus G1, 2, and then G1, 2, that's a G1, 2 squared. Of course, that's just the determinant of the metric tensor, right? So this is going to be R1, 2, 1, 2 over G, where G is the determinant of the metric tensor, right? So this thing over here is just, that's the determinant of the matrix Gi, J, the metric tensor over there. Excellent. So now let's recall, of course, what's this is for the sphere, right? So we've previously proven that for the sphere, you have this metric, ds squared is d theta squared plus sine squared theta d phi squared. And we proved in a previous video that R1, 2, 1, 2 was just sine squared theta, right? So what will the curvature of the sphere be? The curvature of the sphere is going to be sine squared of theta over the determinant of the metric tensor. Of course, the metric tensor in spherical coordinates is exactly a 1, a 0, a 0, a sine squared, so the determinant is just sine squared. This is for the sphere, of course. And that is just 1. So we've just proven the Riemann curvature of a sphere is equal to 1. Now, it's important to realize that the scalar curvature of the sphere, we found the scalar curvature of the sphere was equal to 2. And so now we see that there's a relationship, at least in this specific case, between the scalar curvature and the Riemann curvature. In fact, it looks like the Riemann curvature is exactly half of the scalar curvature. We're going to see in a further video the theorem of Gauss, which relates the scalar curvature and the Riemann curvature in the two-dimensional setting, and basically in a couple other special cases. So this tensor over here is going to give us our yet another curvature invariant that's going to be helpful to understand geometric properties of manifolds. Thank you very much.